Hello everyone, my name is Stefan Lindy and I'll be starting us off with the motivation behind our project, partially electrified single-aisle aircraft. Today we will walk through why the system is needed, the mission constraints that drive the design, how the aircraft operates throughout a typical mission, and why you should fund our project. Our team is organized around key system engineering roles. I served as mission requirements lead, defining the operational objectives and constraints. Graham led trade studies, Kieran focused on risks, Noah managed MBSE, and Ayush overlooked each discipline. The need for a hybrid electric regional aircraft comes from three converging pressures. First, global aviation emissions continue to rise. International bodies like ICAO and IATA are pushing for meaningful reductions by 2050, especially in regional aviation where many flights are short, frequent, and fuel intensive. Second, airlines are facing increasing financial pressure. Fuel represents 20 to 30% of operating costs. Volatility in fuel prices motivates operators to pursue lower burn propulsion options. A hybrid electric system with a 15 to 30% reduction in fuel burn provides a strong and economic incentive. Third, although interest in electrification is growing, no hybrid electric aircraft is certified for commercial service today. This creates a clear opportunity for an efficient, scope-compliant platform that can serve as a first solution. From a cost standpoint, regional carriers want lower operating expenses without major changes to airport infrastructure. From an effectiveness standpoint, the aircraft must still meet all FAA and EASA performance and safety requirements. And from a coverage standpoint, regional aviation serves a broad network of small and mid-sized airports. Any hybrid electric aircraft must remain fully compatible with current infrastructure. Current turbofan platforms like the E175 and CRJ series offer proven performance but rely entirely on conventional gas turbines. Turboprops such as the ATR and Dash 8 are more fuel efficient but still limited in emission reductions. And although early hybrid electric concepts like Heart Aerospace's ES30 or Embraer's Energia series show promise, none are close to certification. This highlights the technology gap we're aiming to fill. We aim to design a cost-effective, low-emission hybrid electric aircraft that stays within scope clause limits. We produced a complete system-level design covering propulsion, batteries, thermal management, and aircraft integration. And finally, we generated the operational concept, cost assessment, and support infrastructure needed to meet FAA and EASA compliance. These goals are shaped by quantifiable emission constraints. The aircraft must maintain scope clause, achieve nautical mile emission range to match current regional routes, provide at least a 12% NOx reduction and meaningful fuel burn savings. And just to note, these are just a subset of the full mission constraints that from our technical requirements, but they represent the dominant design drivers. To understand how the system operates, we developed a CONOPS. The aircraft begins with pre-flight checks and electric taxi, uses hybrid assist during takeoff, transitions into an optimized hybrid cruise, captures regenerative energy during descent, and wraps up with electric taxiing, battery recharge, and system reset. This ensures minimal operation disruption for airlines while enabling emissions and fuel burn reductions. I'll now hand things over to Ayush, who will walk you through the problem definition and how these requirements translate into system needs.
Thanks, Stephen, for giving us brief about the goals and the needs of hybrid electric regional aircraft. Now, in order to define the problem, we first need to be clear about who we are designing for and what they actually care about. On this slide, we have grouped our stakeholders into three buckets. On the left are government and the regulators. Their core need is safe certifiable systems. In the middle is industry, OEMs, airlines, and operators. They need low cost, reliable operations. On the right is the passengers and energy providers. They are asking for quieter, cleaner flights with trust in hybrid electric safety. We take these high-level stakeholder expectations and run them through our QFD process, which turns them into explicit requirements and ultimately quantitative design targets. Now we move from who to what those stakeholders are asking for. We combine inputs from customers, operators, and regulators to build this requirement list. The main themes are cost, safety, reliability, comfort, and airport compatibility, with scope clause regional jet missions settling the baseline performances. Finally, once we introduce hybrid electric, new requirements appear, such as fast charging and turnaround, safe and certifiable batteries, etc. Now these customer needs are translated into engineering characteristics we can actually design to. They are anchored in current safety standards, regulations, and regional jet performance, so we stay certifiable and competitive. The main levers are range, takeoff and landing distance, fuel burn, NOx, and exterior noise, plus hybrid specific targets. Together, these characteristics define the measurable performance envelope our hybrid electric aircraft has to meet. Now these engineering characteristics are mapped against the customer requirements in a QFD relationship matrix. The left matrix shows how strongly each requirement drives specific technical parameters. The correlation roof on the right then reveals the key trade-offs and the synergies between these technical parameters. For example, how pushing range or power may hurt weight, noise, or cost, so we can see where improving one metric helps or hurts another before we set final targets. Here we move from relationships to what really matters most in the design. Top drivers are certification and safety. Medium priorities are operating cost and overall performance, and lower priorities are passenger comfort items like interior noise, cabin styling, and baggage volume. Finally, the tech difficulty row shows that the conventional metrics are relatively easy to achieve, while hybrid-specific items such as batteries and charging carry higher difficulty and will dominate our engineering risk. Now that we have set requirements and priorities, this slide shows how our concept benchmarks against the E175, CRJ900, and ATR72 in the same scope clause market. Capacity, runway performance, airport compatibility, and pilot interfaces are kept comparable to today's jets. We concentrate technical risk in the hybrid electric elements, thermal management, and fast charge infrastructure so the aircraft feels familiar to operate but adds new technology where it really moves the needle. Using QFD, we set clear targets for a hybrid regional aircraft that stays compatible with today's routes and airports. We kept regional jet performance like Mach 0.78, 1300 nautical miles, and standard takeoff landing while meeting all the safety and environmental goals. Battery and cooling targets focus on high life cycle, strong power energy performance, and fast like 50 to 60-minute charging, and high dispatch reliability. Overall, QFD translates stakeholder needs into practical low-risk design that improves efficiency and emissions without disrupting current operations. Now, we will move towards Noah, who will walk us through establishing values. Thank you.
Thanks, Aish, for explaining how we've defined the problem we're trying to solve. Now we look to establish value through the solution that we come up with. So as discussed during the QFD section, each of our requirements kind of fall under different themes. And so for our MBSE work, we've grouped all of those requirements into 11 key groups as shown in the blocks on screen. Now, these high-level requirements branch off into a lot more detailed requirements, which obviously we can't show all on one slide, but we do get all the way down to the level of defining specific target values corresponding to the ones that I just discussed. Now to go a little bit more in depth on our system decomposition. So as you can see here, we have 8 key subsystems defined for our MBSE work. These subsystems contain all other relevant subsystems, even if not directly mentioned, but you'll see that the propulsion subsystem is the biggest block out of the 8. That's because a lot of our development is happening with that subsystem being a hybrid aircraft, so we have that more fleshed out to account for that importance. But all of the other subsystems are important to account for weight and power, which you'll see when we get into our parametric diagrams. Here's the FFBD that we defined for the propulsion system. This assumes that we're looking at a parallel or series hybrid architecture, but obviously is subject to change if we go a different route. But effectively what is being shown here is the balance between electrical power and mechanical power being provided to the turbofan. And then if necessary, we have some power that goes to a generator that allows us to recharge those batteries. Since weight is incredibly important in aircraft design, that was one of the allocations that we used for our MBSE work. So here you see how we have weights for each subsystem that are effectively totaled up and output as a system weight. And the importance here is with our scope clause requirement, we can verify that different allocations of weight across the subsystems meet that requirement. We also do the same thing with system power, since that's an important factor in hybrid electric aircraft design. We take power draw for each relevant subsystem. Not all of them are included here, but those are again totaled up and output as a total system power. And while we don't have a direct requirement for that, we can check and make sure that the total power output is somewhat reasonable. In addition to the allocations on the previous 2 slides, we also have a few here that look at some derived requirements and allow us to study the propulsion system in more depth. So one is power per weight, which is an explicit requirement, but we can use calculations for the system power to look at that and then also account for a propulsion system weight. And then the propulsion system available power and stored power are based on the architecture shown in the FFBD, where you have a certain split between the turbofan and the generator. Now I'll hand it off to Graham to go through alternatives and trade studies.
Thank you, Noah, for presenting about the subsystems. I'm Graham, and I'll be presenting the morphological matrix and more details about our down selections for our subsystems. On the right here, you can see our morphological matrix. We have several options listed for each of the subsystems required on an aircraft. And we kind of selected ones that would most align with an electrified aircraft. So in the top, propulsion system, and then going down, we have the ground taxi system, the electrical storage system, the aircraft size, the main mission, and the wing configuration. I've bolded all of the options we selected, most of which kind of based on the team's analysis, but I'll go into detail on the propulsion subsystem and how we selected the parallel hybrid architecture on the next few slides. And the kind of goal here was to select the total architecture as a whole system. So like what aircraft size and mission lines up with a propulsion system and a ground taxi system that all makes sense as a sum total. To give a breakdown of the powertrain alternatives or power subsystem, we've identified three main concepts here for an electrified aircraft. Firstly is a parallel hybrid system using both a gas turbine engine and an electric motor coupled to that fan or turbofan, and using that to drive the fan. Also a series hybrid system where there is a generator feeding into a battery with a distributed propulsion system. So multiple fans, one turbojet engine or one turboshaft engine powering multiple turbofan configurations. And then kind of the biggest concept is the partial turboelectric with a series and a parallel system integrated. So this has a turbofan engine with a generator attached, as well as two motors and likely battery on board to kind of route power as needed depending on the flight envelope. Kind of the most complex system, but also the most efficient. Going into the trade study of the power systems, we have four alternatives considered, including a baseline conventional turbofan on the left, and then the evaluation criteria. As mentioned earlier, the fuel burn is really the key driver of any engine architecture selection. You typically want to see a 15 to 20% fuel burn improvement in order to justify a new aircraft in the aviation industry, and as such, we've weighted it quite highly. We also weighed the operations and maintenance cost quite highly as 20%, as this is really the driver for if airlines will want to buy the plane. And then going down the list, we have the system-specific power, kind of how much power per weight we can get, 15% for the reliability and redundancy of the aircraft, 10% for kind of the flexibility of the propulsion system across the flight envelope, and then 10% again for the technology readiness level. How ready is it to enter service? For the propulsion trade study, we looked at all of the previous criteria and weighed them accordingly for each subsystem. As mentioned before, this series parallel hybrid was the kind of king of fuel burn. However, you can see at the bottom, it has the tech readiness level of 1, which kind of dropped it down as far as being able to select it. I'll focus on the parallel system we have here, which had the fuel burn improvements as well as the system-specific power, which really drove it to a high score. You also don't lose as much reliability or system flexibility with a parallel hybrid system, as well as the technology being somewhat more mature than the series parallel hybrid. As a result, based on this weighting system, we've down selected the parallel hybrid architecture as it met our needs more for this aircraft. So to kind of summarize our trade studies, we down selected a parallel hybrid architecture after weighing several of the key factors that airline customers would like to purchase. The parallel hybrids architecture really represented a big reduction in fuel burn while also maintaining good adaptability to the MRL and TRL of the current industry. And as a result, kind of seems like a great opportunity for an aircraft to get made and one that airlines would like to buy. Next, I'd like to welcome Kieran to talk about our final selection.
Thank you, Graham. My name is Kieran Holton. I'm another one of the system engineers in the project, and I'm going to go over the concept. So this is our concept for Hera, which is a conventional low-wing layout featuring a large rechargeable battery at the root of the wing in the fuselage, which provides best stability given the weight of it. And you can see our advanced hybrid open turbofans featuring 7 blades for noise reduction, and the frame is going to be a modern semi-monocoque fuselage with a glass cockpit. When we talk about the preliminary weight and balance, most of the airframe weight comes from the frame itself, with also large components coming from the power and prop systems. When we talk about power, we get a total of 32.8 megawatts, which is similar output to a traditional airframe using a gas engine. When converted to horsepower, the hybrid system allows us to offset weight by undersizing our propulsion system with hybrid boost, and also some of our modern manufacturing methods and electrical systems help offset weight. When it comes to V&V for this project, our approach is to help buy down flight test risk and cost with inspection, demonstration, and analysis, verification of tasks. However, being that we are a passenger aircraft, a lot of our test points are going to be required to be done with flight tests to prove airworthiness to the FAA. And our goal is to run a robust safety first campaign at a reasonable cost as we approach market. When it comes to risk posture for Hera, our goal is to take a very conservative risk posture as expected for commercial aviation. Risks were evaluated from both a programmatic and powertrain point of view on consequence and likelihood, and the team will work going forward to buy down risk through working with our contractors, developing technologies, and being conservative with the schedule to hopefully see risk moving left and down on this chart you can see in front of you towards the dark green. Finally, we want to talk about why we believe Hera is the platform going forward and what about it is special and why it should be funded. So it addresses a gap in the regional aviation market servicing airports that are currently underutilized. It helps as an airline lower emissions, carbon footprint, it lowers your cost through fuel, and it quickly integrates into the fleet because it is designed to align with typical regional aircraft of current day. Also, it helps bring electrification technology into modern commercial aviation, and its engineering practices that we're implementing will help reduce development and time to production, allowing it to come to service quicker. And this is why we believe Hera is the platform for you going forward. Thank you for your time today.